thank you so much for coming today. I appreciate it.
You're welcome.
Space has kind of been, and astronomy has been a big passion or interest of mine, like throughout my entire life. And it's so funny how so many kids and then adults just have this interest in space and astronomy. It's so interesting because it's one of those things that it's kind of like, it's almost like dinosaurs, astronomy. It's these things that stay with you from when you're a kid to when you're an adult, and the mysticism behind it never goes away because it's so, I guess maybe because in the large scheme, it's like we know so little about it, I would assume.
Right.
But thank you for coming today. And if we could start with you kind of giving me an outline of where your passion for astronomy kind of started and what got you to where you are today.
Okay.
Yeah.
I can remember very clearly yet in my mind. I was in 5th grade, and I went over to a friend, Craig Hodges' house one night, and his father had a telescope set up, and I got to see Saturn and Jupiter through it. And I was like, wow. I mean, these really exist, and there it is. Of course, it was it was probably about a 5-inch telescope, so it wasn't really shabby, but got a image, and I could see some moons on Jupiter, and I saw the rings of Saturn. And so that just like, wow, I want to know more about this. So I had that passion, and then I majored in physics in college, and then I was going to graduate school, and I wanted to go into astrophysics. And the professor I wanted to work with at Purdue went on sabbatical shortly after I got there, and then never came back. And they didn't have somebody else at that time in astrophysics. So I went into theoretical high energy physics, which oddly enough is connected to astrophysics now. But I worked in that, and then I got a job here at the University of Dallas, and I luckily was able to sort of switch my research area because undergraduates can't do research in theoretical high energy physics. It's just mathematically too beyond the average undergraduate. And I worked with some people at UTD for a while, and then I got a grant and decided, well, we're going to start buying equipment. We're going to start having an observational program and develop astrophysics. So I was able to do that and keep doing it. And so it's interesting. I took astrophysics in graduate school, but I've learned so much more since then, as we always do. I think you would share one of my bylines that I put in my email that is on Coro and Paro, I'm always learning. And so I try to learn from every interaction I have with people. And sometimes we have to teach ourselves a bit, but we keep on learning about the sky. Now that interest you said that everyone has of dinosaurs and stars, I think I like to tell students that we are the creatures that anthropos is those who look upwards. Other animals don't look up in the sky. I've seen my dogs once look up in the sky when there was a hawk or something, but they don't ever notice stars, and animals don't do that. And I said, and also we're on a planet where our whole being is vertical. We can grow upwards. We can use 2 feet to support ourselves and not 4 feet. If we were on a larger, more massive planet, we'd probably be quadrupeds and walk around, I like to think like Komodo dragons, and we'd be looking side to side. We wouldn't be looking up at the stars.
Right.
So it's very fortunate that we're able to look up there and see them. And I guess it's just, we wonder. I got a email from a former student of mine from a long time ago who's in Florida Keys, and she mentioned that she was up in the morning and saw Orion. And she said, I'm so glad I learned all these constellations from you and even more about what's going on with them. And I always considered Orion one of my friends, so it was good to see him in the sky. And the funny thing is, I noticed a couple weeks ago that he was up when I walked my dogs, and I consider him a friend too. So it's kind of a cool thing that we associate with the stars that way as well.
Yeah. So you were able to locate Orion in the sky, and with the light pollution that we have, is there or we're limited?
There's enough bright stars in Orion
Yeah.
that we can see. It's one of the brighter. I think it's probably the brightest constellation in the night sky. So overall, we can see them. In fact, a few years ago, you might have read that Betelgeuse, which means armpit of the mighty one, as it is in his armpit of it, is a supergiant, red supergiant star, and it dimmed, and astronomers are kind of wondering, is it going to explode? What's going on? What's happening? And I had noticed, it was noticeably with your eye, could see it was dimmer than it had been. And finally, it was determined that it, as this red supergiant has so many different nuclear processes going on inside, had puffed out some matter, and that big cloud, as it cooled, happened to be in a longer line of sight. And just like a cloud would block out light, it blocked out some of the light. And so, but it was a big mystery. People thought, is there a binary? What's going on with it? But finally, I think everyone agreed that it was just matter ejected from the star itself.
And that would be when you suggested that, the idea of binary, another star that it could be close to, like one of your areas of expertise, right? The cataclysmic variable stars.
Yeah.
Is that right?
So binary would be a star that, two stars that are gravitationally bound to each other. So they're orbiting each other. Right. Sometimes they can be really far apart, but I'm more interested in the ones that are really close. And so they thought maybe there was this one would have had to be a far out companion and never been observed before. But that hypothesis got rejected eventually.
And what happens if two stars that are too close together get too close? Is there some? What can happen?
It's cool, and this has intrigued me. By the way, I have to say one thing is I've learned never say never. And when I was applying for jobs, I was in Indiana, and so I had this job in Texas, and I thought, I never wanted to go to Texas. I don't want to go to Texas. Well, I'm so glad I came here because I think I've had a good career and I love the university. And also I thought, I don't want to study binaries. Binaries are just so weird. And then, I love binaries. I just got into it.
You got to open yourself up to these things sometimes, right?
Yeah,
sometimes you don't know.
Yeah, exactly.
Like I tell my kids, you always got to try the food. Even if you don't like it, you got to try it. It's the same concept, right? Even as adults, we're kind of closed off to the ideas of change, right? The fear of something new.
Yes.
So you go off and try it and you realize, wow, I'm meant for this, or this is like, you takes you in desired spots you didn't think it could take you.
So the binaries I like, cataclysmic, are usually, the stars may be, if you had the sun as one, the other star is bigger, a little less massive sometimes, and where they're almost touching. And orbiting. So they orbit in hours. So you have to imagine something the size of the sun going around in an orbit in an hour. It's just, it's just hard to imagine what's going on there. Right. And the most exciting ones are one where one of the stars has evolved and it's become a white dwarf. White dwarf star is basically a dead star. It's shed all of its outside structure, and it's just the core that remains, but it doesn't have any nuclear reactions going on anymore. It's just heat that's left over. And it's very dense. It's mostly carbon, and it's compressed. So I tell students it's a diamond in the sky, literally. And that's about the size of the Earth. So now you have one of these stars the size of the Earth, which is small. And so this other one's still, what used to be very close to the star, is now out there. So it's a little but since the mass of the white dwarf has remained pretty much the same, that period is still going to be on the order of 2 to maybe 4 hours. And so, and in that process, once it shrinks down, matter can start to flow into the white dwarf from the bigger star. And it just kind of takes a spiral path and goes around and forms a disk around it. So we try to study the disk. And the only thing we have to observe, because you can't see these things. Right. They're so far away and so small of a structure so far, we only look at the light coming from what's happening to the light. And you see variations in the light. Sometimes it's going to be from the disk itself. So most of the times you see the two stars, and then you try to determine what's going on with it. So it's a challenge. It's a game to figure out. I think that's what science is always about. It's like to unravel what's going on there. So I like those. And then eventually enough matter could spiral down onto that white dwarf and cause it to just not implode, but to detonate all of the carbon at once in nuclear reactions, and it becomes a supernova, a type 1a supernova.
And would it need that binary star to do that, or it can do that?
No, it needs the binary.
It needs the binary. Wow, okay.
If it's an isolated white dwarf, it's just going to eventually become a black dwarf. When it cools off, you won't see it anymore. And that's going to be, probably 5-10 billion years, so it takes a long time. But if it's got a companion, then its evolution is changed.
Right. It's probably staying warm as well, obviously. Yeah. It's keeping the heat going. So, and the disk that you mentioned, what is the disk made of as far as? It's,
the outer atmosphere of this other star, which has started evolving itself, so it's bloated up a little. And so it's mostly hydrogen that comes out, because that's stars like the sun even yet is mostly hydrogen.
Right.
And so that gets pulled, but not really pulled. There's something called a Lagrange point. If you have a stick with two masses on it, or a teeter-totter, the middle of the fulcrum. But if you have two people of different weight, they have to sit at different distances to balance. And so that center of mass is where the fulcrum is, and then you have to adjust to make it balanced. In there, since they're orbiting each other, the point where it balances is not the center of mass. It's something we call a Lagrange point. And in that Lagrange point, when the secondary star swells up, when it reaches its envelope around, it's called a Roche limit. Sorry, I'm getting very technical.
No, this is...
But when it reaches it, matter then just kind of gets siphoned off through that Lagrange point. So it's really through this one point, and it goes and escapes that star then, and is now orbiting the other star.
And that's what creates the disk. So it's like a light disk of helium, and so it's constantly being fed by the star. So it's So it's constantly just. It's not like it's being generated or having anything to do with the white dwarf in that sense.
No, it's fed from there, and then. Because there's friction in the disk, material will start to slow down. It slows down. It goes in smaller orbit towards the white dwarf. And eventually it can accrete on the white dwarf. And sometimes when there's enough, you get hydrogen fusion. Again, it becomes a nova. So a nova is tied to this. And before that happens, if the disk is disrupted and becomes a little brighter, that's called a dwarf nova. And then, of course, when enough matter accretes onto it in a fast enough rate, then it can become the supernova.
Supernova. Now, when larger planets explode and become either what would be a black hole or be a
neutron star,
how could that white dwarf turn into either of those two?
No,
it's not possible. It's not large enough, not enough, and not enough.
And the nuclear reactions are the whole structure of the star is entirely different than the others. The others are called core collapse supernovae, or type 2, and those are just gigantic stars that everything eventually the core builds up to iron inside, and iron you can't fuse and get energy out of. So the star suddenly has no energy, but it has all these layers of all these other elements pushing down on it. And it literally collapses and bounces off that core, which very quickly gets changed from iron to all neutrons. And what we see as the supernova is the matter kind of bouncing off, going off into space, colliding with each other and the stuff out there, producing more light, but also producing all of the elements, pretty much all of the elements heavier than iron that we have on Earth and otherwhere. So that spewing out enriches the galaxy in the nearby region with these heavy elements.
Very cool. And I do want to come back to the collapsing of a star, coming back to, and then talk about black holes, which I think is like one of the, that's like when you ask, I mean, I've told some of my students, my younger students, that I was going to have you on, and like I had students just, they were like, that is so cool. They're just, and their idea of, black stars or black holes is one of the phenomena that everybody loves, and there's so much mystery behind that. I want to come back to that though, and first continue to focus on your areas of expertise. First with the cataclysmic variable stars. Through your research, what have been some of the most, in the last maybe 5 or 10 years, the most biggest insights that have come from researching those stars? Yeah.
Okay. Yeah.
That might be too general of a question. But
no. Actually, it's a really.
You mind bringing that into a tiny bit? The microphone, you just pull it to it. Yeah, perfect. That's good. Yeah.
It's a very good question because, we're doing this research that's way out there. There's nothing near us, and people say, "Well, what's the benefit to us?" Well, the benefit is that we're getting more insights into how the cosmos works. I'd have to say that's it. And also it's helping us describe where these elements that build up planets can come from in these supernovae. So I would say the insight we've gotten is first of all, to explain something that we found out there are these binary stars, and the ones that have even shorter periods, ones have longer periods, and there's been this gap around 2 hours, and we never find any there. And that was a big mystery, which only got solved about 10 years ago, 15 years ago. So this is part of what we call understanding the evolution of binary stars. So it's kind of given us a better understanding that there's a very coupled evolution. It's not just one star then one star, that they can both exchange mass and do things and have a lot of weird behavior. So I would say it's more for understanding fundamental processes that can be going on here. The other thing that I have gotten more interested in is binaries with planets around them. So one of the things is we'd love to find is a cataclysmic variable star with a planet around them. Haven't done that yet, but we'll probably get to that soon. I have a colleague who's just visiting on Monday, Michelle Montgomery from the University of Central Florida, and we found some weird signals. Not meaning aliens or anything like that, but just that. I mean, we racked our brains for years, and finally think it was probably a planet that got ripped apart somehow, and we're seeing it moving around this binary system. And there's chunks, though. It's not just one planet. There's these chunks. And so we wrote a paper on that, and the referees kind of said, well, we don't know if you can really assume that, and we're in the process of arguing our point more strongly.
That makes sense, yeah. Yeah, that's, when you said you measured, or you got some, how do you measure the information that comes in? Through sound waves, or?
No, this is the other thing that to me is even more amazing. When you observe stars, there's two major types of analysis you can do. It's all with light. Light is the medium. Light is really the narrator of the story of the evolution of the whole universe. Because, for example, the James Webb Telescope is very popular now. We're getting neat pictures, but it's also taking us back in time closer and closer to the first stars and the first galaxies too. So we're using that light, which has been stretched out because the universe is expanding. So the wavelength has changed. And so it has to look at a much longer wavelength than what it would have been created as. So the light, it can be analyzed in two ways. One is just changes in the intensity of the light. So I like to tell people, if you're looking at a planet around another star, an exoplanet, that if the planet is going right in front of the star and you're towards you, so it blocks out the star at times, we call that a transit, we can detect a planet so small around some of these stars. It also depends how far away are they. But it's a lot like if you were walking down a road and there was a car a mile away and a mosquito flew across the headlight. That's what we're detecting, something equivalent. So you can imagine it's not very big change in light. But through technology, cell phones, basically all that technology came out of research in astronomy to develop better cameras, that we can do these very, very delicate measurements on changes in the intensity of light. So that's what I work with.
That's impressive.
It's called photometry. And the best ones, we do some from Earth, but the best ones are taken by space-based telescopes now, like Kepler, which is no longer functional, and now TESS. And James Webb does some as well. But the James Webb does mostly the other type, which is called spectroscopy. And that's taking the light and breaking it into the colors that are there, the wavelengths that are there. Because we're going to find in those wavelengths signals of different gases. And that'll tell us the component of these. And also, if the stars are moving, the wavelengths shift a little. It's the Doppler effect, like when you hear say police car go past you and the sound, goes, the pitch changes. And so the light being a wave does the same thing. And if it's a binary, it's going to go up and down and up and down. You can get those regularities in the signal too. So spectroscopy is really good. It's really hard to do though.
Wow.
Because you have to pass the light through a slit and break it down into those component waves, and you lose a lot of the brightness, and it's not very bright to start with.
I see.
So far. So you need space-based telescope or a pretty large telescope. The diameter of the telescope is a measure of the size. You need at least a 2-meter telescope to be able to do on Earth some spectroscopy, and those are probably getting up to $500,000.
Yeah, that's 6 feet of lenses of lens. That's impressive. As far as using light as your main measurement or for identifying different phenomena, how does that play in measuring the age of the universe? In that now I think it's 13 billion years is what we think.
13.7.
And so is that how that number was how scientists came across that number?
That's one of the earlier determinations. And now we have other ways. There's actually about 3. One is called acoustic baryonic vibrations, and which doesn't tell you much. But what it is it's kind of the universe started in this hot Big Bang, incredibly dense state. I like to say it's about the size of a proton. And you have everything we know in our universe compressed into there. And why is it compressed in there? Because it was all energy then. Energy doesn't take up room, matter does. So if you have a light on, it doesn't take up any room in here, but your furniture is taking up the room. Right. So when it was all energy, it was incredibly hot. And through this event, the Big Bang, it expanded, and space and time were created as well. That was kind of the vessel holding it. That all expanded outward, and the gas cooled. So I always like to tell people, if you take the back of your hand and you go, it's warm, but if you go, it's cool, and it's same air coming out of your lungs. It's just that the expanding air, when you have a smaller opening it comes from, cools. And so that's what the universe did. It started cooling off, and the time when it got cool enough for electrons to bind with protons and form hydrogen is what we look at that, what was going on then, and how the matter was distributed. And those are those acoustic vibrations. That is one way that is determined. The other way, and probably the more basic way, and I should probably have said that first, was what Hubble did. And he studied thousands of galaxies and noticed the farther away they were, the faster they were moving away. And he measured the moving away through that Doppler shift again in their spectra. And the distance you can measure by other means. And so he got Hubble's law, which is a straight line relationship between the speed of a distant galaxy moving away from us and its distance. So that's a fundamental thing. And then the slope of that line basically tells you the Hubble constant. And then you say, well, how long has this been going on? Well, we know that time is going to be distance over speed. Mm-hmm. And so you take basically the slope of that line and 1 over it, and that gives you the age of the universe. And then it gets refined by much more complicated models.
So how far out can our most advanced telescopes see? And what factor of time is that? Like, say we can see as far out as however far away that is, how much, because obviously the light that we see from the stars is in the past, right? So how far in time can we see? Yeah.
Yeah. Cosmologists. So now we go into the area, it's called cosmology, not just astronomy, but cosmology, particularly related to the structure of the universe. They usually measure things in Z, which is a redshift, how much the light has been stretched, because you and I and light and the whole universe exist in space-time. And if space-time is literally expanding, the wavelength of light expands. And so that light becomes longer wavelength moving towards the red. And so they measure that cosmological redshift from it. And so basically we can look back right now to almost 13 billion years.
I see.
Which, of course, then you get into this whole thing, well, but time is being changed because light's being stretched, and so, but we leave it as kind of thinking it was a bit more static, and we can just go back, and it's about 13 billion years.
That's crazy. So we can see close to the edge of the universe.
Close, yeah, close. Well, not to the edge of the universe, but in time. In time, we can see. Yeah, the edge of the universe is another question.
Right.
We don't know right now. It may be that the universe is infinite.
Right. Those are those kinds of thoughts that just like can make you go crazy.
Yeah.
It's just like the idea of before the Big Bang, it just there being pure energy. Like the understanding of, how is that energy there? Yeah. And it's kind of scary because there is no way to know.
Right.
It's just it's just those kinds of thoughts just throw me for a loop.
and what impresses me is that we humans can wrap our brains around it and make these models, get information, develop the technology to advance it. And it's like, I'm pretty impressed with people.
Oh yeah. I mean, again, I love the ideas of planets and astronomy, the idea, the math behind it, and the fact that you have scientists and professors and researchers who can use math to answer questions of the stars is just, it's amazing. Yeah. It's just, it's insane to me. I'm just a musician, so it's on another level for me as far as that goes. So you mentioned exoplanets earlier, and that's another area of research that you've delved heavily into.
Yeah.
Can you explain what an exoplanet is?
Yeah. Basically, an exoplanet is a planet. It can be rocky or gaseous that orbits another star other than the sun.
So anything outside of the solar system,
right,
essentially.
Outside of the solar system. And we've had Kepler was a very, very successful mission, which got extended beyond its lifetime. Most of these space-based telescopes last longer than we imagine, or they were made to. And so Kepler had a second campaign called K2, and it was running out of propellant to kind of keep it oriented. But clever engineers realized they could use sunlight and the heating to help that, and therefore had a bit more limited target as it went around, but you could still have it focused long enough to start getting data on these things. So that was really cool. And TESS now, which is the Transiting Exoplanet Survey Satellite, has replaced it. And so there's probably, Kepler alone had probably verified, I think, at least 2,400 planets. Wow. So first is discovery, and then it has to be verified, which means observed again in different ways. And
right.
So Kepler has was very successful in that. And TESS now has maybe a few hundred identified, but about 4,000 waiting to be confirmed.
Wow.
And it's just getting the people to do these things is what becomes the difficult thing, because we get a lot of data. And,
right. Do you think that, or how many stars do we think have exoplanets?
Yeah, that's a good question. Long time ago, we thought planets were really rare, and then once we start observing them and seeing, wow, there's a lot more, and we're finding not just a planet, but sometimes 5 planets around a star, and then there's probably more, because we're only seeing through Kepler and TESS the ones closer in, so there could be ones farther out. So now we think that probably every star has planets.
Wow.
And when you look at it in our galaxy is probably on the order now, maybe say 200 billion stars.
Wow.
And then each of those stars probably has maybe 10 planets. So we get to 2 trillion planets in our galaxy alone.
Just in the galaxy.
And then we have another 200 billion galaxies. I mean, so it's,
statistically speaking, there has to be life
right,
outside of Earth.
Right.
There has to be,
yes,
right? I mean, and this is another part that's fascinating. And I don't know how much of your areas of studying exoplanets has had you have these thoughts about there being alien life, because it's so fascinating if there are other beings that are, first of all, what's crazy is that from our understanding of what creates life is we need certain conditions, right? Water, nitrogen, all these things that make life, which is fascinating in the first place. When you have a combination of these elements put together, it necessitates life. That's just a crazy thought to begin with. But then, okay, what are the chances? So back to the ones you've studied that you know of, how many of them have, or what are the climates of some of these? Like, have we seen any elements that may say there could possibly be life on there, or there are elements that could lead to life, like water, et cetera?
Oh, yes. And that's where now James Webb Telescope is coming in, because it can actually measure the spectra of atmospheres of these exoplanets. Once they're identified, it goes and does this. So it's, I have to say, it's still in its infancy, detecting the elements in atmospheres, but I think it's improving. And so we look for water. We look for carbon dioxide, are probably the 2 things. Methane would be another thing. Something that could indicate some kind of biological processes that would produce CO2, and at least biological processes we understand
right.
Could produce these things. And there are a few planets where we've observed, few meaning count them on one hand, but they're there that we think. And the other exciting thing is they're not so far away. They're not thousands or millions of light years away. They're on the order of maybe, say 50, 100 light years.
Oh, wow.
So they're relatively close in.
Sure.
And that's another thing. And I want to interject one little thing that I'm semi-serious with this, is that one of the reasons we're looking for exoplanets is we're looking for a new home, because our star, we know, is going to eventually become a red giant a couple times. Even the first time, it's probably going to cause things to burn up on Earth, the oceans to evaporate. The second time, definitely, when it stretches out to the orbit of Venus. And
so we'll be cooked. We'll be toast.
Yeah, we'll be toast.
And in how many billions of years?
About 5 billion.
About 5 billion. So we got some time.
Yeah, we got some time. So we're starting now early to find. But it's a sobering thought to realize, and sad, because of all of the life we know on Earth, all of the diversity of plants and animals will be gone.
Yeah.
Then so we are desperately searching for Earth-like planets. The ones, though, there's a couple, well, maybe 5 that are Earth-like, but they're more massive than Earth. We haven't found kind of the right mass. So they would be, I think, usually 5 or 10 times more massive. So if it's 5 times more massive, gravity is going to be more than twice as strong. So we had better work out and be able to support our weight.
Yeah. Well, are there, could life live on that? If they'd evolved to that?
If it could. Definitely.
Right.
Yeah.
So it goes to show. So first, these planets that you said were on those handful of planets that you identified. Is there enough data to say that there is life on there, or is it just, we know that there's water, but we just don't know how much. We don't know the fact that there's 5 times gravity. For example. Is there enough to say that there could be life, a good chance, or not really?
Yes, I think we can say could be, but we can't say there is.
Right. Yeah. And there's no way to quantify the statistics of what it could be. If it could.
It's unless we get a signal beamed to us from somebody or something, we don't know. But on the other hand, you might know that there's new missions going out to Europa and maybe another one to Enceladus, but those are icy moons. Europa is around Jupiter and Enceladus around Saturn, and they're icy, but we know they have oceans underneath, and we see geysers. And so we want to know, is there life in those oceans? Right. So the big thing will be to actually sample the water and examine it and see if there's some kind of life in there. So that's another aspect that is exciting. So it's just amazing. In the last 20 years, astronomy and astrophysics has just exponentially grown. I mean, it's just because we now have this technology that gets us all of this information.
Yeah. Well, we think if we look talking about dinosaurs like we were earlier, the fact that there were such massive beasts living on Earth, 65 million years ago and before, because they adapted to the planet as it was then, goes to show how different life could look like on an alien planet.
Right.
And, through evolution, you could have these, it could be hominids that maybe look like us that walk on 2 feet, or, the idea of, how advanced these creatures could be is awesome to think about what they could be, if they could be, or not even, small forms of energy that are just floating, communicating with each other without speaking, just as far as the idea and the fact statistically that there's so many planets out there now that we know could possibly necessitate life. The possibilities of what could be are just endless. It's kind of cool to think about.
And I was just going to interject, and because you mentioned dinosaurs, well, if we didn't have that asteroid hit us 65 million years ago, we might have intelligent dinosaurs. And so maybe on another planet, there's intelligent, dinosaur-like creatures.
That's really cool to think about.
Yeah.
There's one of my favorite movies, sci-fi movies, is Prometheus, which was a really great movie in that where, at the beginning of the movie, their intelligent life put essentially their DNA on Earth. And that's what started life on Earth. There's been this sudden this is kind of alien related, but there's just been sudden surgence of information in the media saying that pilots have noticed possibly alien crafts coming to Earth. Is there a chance that there's always a chance, but is there a chance that some of these planets that are relatively close now that we know could visit Earth and we just not know it.
Yeah.
Yeah.
Okay, I'll tell you 2 stories, if I may, connected to that. One is when I was in high school, between my junior and senior year, I went into a program at Northwestern University. And it was like for you to take classes in calculus and physics and engineering and to see, if you're interested in any of these things. Well, I had an astronomer, J. Allen Hynek, gave us a lecture. And he was head of Project Blue Book back in I guess it started in the 40s. It's the first investigation of UFOs. And so I remember after his lecture sitting and just talking to him, hanging around. And so he was glad to tell me about his work. And then when I started at the university here, I invited him down to give a talk about what it was like to go into this area that a lot of people thought you were crazy, but he was interested in the science of trying to document, put things on a scientific basis, which is what I had admired. But he told me a story that there was the Betty and Barney Hill. I don't know if you ever heard of them. They're this couple, and I think it was in Indiana or Kentucky. They're driving, and supposedly there's this bright light. And then the next thing they knew, they were like on a table, and there were these aliens with the wispy eyes.
I've heard this, yeah.
And then they were examined, and the next thing they're in their car, and that was it. Well, so he interviewed them separately under hypnosis. And the thing that struck him was that their stories corroborated each other. And also that Betty was able to draw a map of stars, in the region as viewed from where these creatures came from, because she had seen this in this room. She has no knowledge of astronomy. And the star that supposedly they came from is it's within, it's about maybe 11, I think it's 11 light years away. So it wasn't like totally out of the ballpark.
Wow.
And so it's Epsilon Eridani was the star and the planet there. So that always hit me like, wow, maybe there was something to it. We don't know. But if I may say, the second thing is the most recent one with UAPs and the congressional hearing. It really hit me just a few weeks ago, because in physics and technology, I show that on the first day, clips, and said, what is this? So let's do scientific method. Look, what could it be? How can we eliminate things? And a couple years ago, the first time I did this, I said, okay, would you like to hear what I think it is? And they said, yes. And I said, oh, class is over. You'll have to come back. And they all went, oh, it was just perfect. And I didn't plan that, but it just was perfect.
That was perfect.
So,
cliffhanger.
Cliffhanger. So this semester, when we were looking at it, I played a clip from the congressional hearing, and the Air Force captain who was, I do not remember his name.
Kolsch or Bosch or something. It starts with a K. But yeah.
Okay. Yeah, he was one of the first to start talking about it, and then he said 2 things that I'm convinced I know what it was. He said, number one, that we had a schedule of things we were supposed to do that day, but that day it was changed, and they wanted us to do more realistic type of surveillance. I thought, okay, so your original mission got changed that day when they saw this. And then the next thing was that this is outside San Diego, the oceans were calm, but then they saw this white water, and they couldn't understand where it was coming from. So I can tell you what I think they are, and I wish I was a member of Congress, because I would have asked specific questions.
Very cool.
And that is, there's something called laser-induced plasma strings. And what basically we can do is take infrared lasers, so you can't see the beam, and they're pretty powerful lasers, and they can be separated by maybe just a few feet. And they go up into the atmosphere, and then you cross the beams. And when they cross, that heats up the atmosphere and creates a heated plasma, literally. If you cross them, you're getting like a tic-tac in the sky. And people don't realize that all of their observations were not visible when they're looking at their heads-up display. That was infrared because they're looking for heat signatures.
Right.
And so that's it. And then, as you also know, if you ever had a laser and a pet, you can move it around real quick.
Right.
And it seems to jump out. Well, crossing those, you can do the same thing and move it around. So I believe it was these high-powered lasers, infrared, that were being crossed, and they're also modulated. You could actually put... Oh, no. Sorry.
That's all right.
Oh, wow. Forgot about mine.
It's all good.
So the beams can be crossed, and then where do they come from? Well, that's the whitewater. I think they were coming from a submarine. And as the beams come up, it's at high energy, they're heating the waters, causing turbulence, boiling, maybe like in the water. And so that was it. So
do you know what submarines would be using them for?
This would all be part of trying to produce these to have incoming missiles follow those signatures and not go to targets.
Oh, I see.
And so it's all a anti-missile defense type plan.
And so what they saw, which looked like those Tic Tacs that just flew from the water all the way up to the what looked super fast speed, was essentially these two.
Yeah. And
Right.
then he said they went way up real fast and disappeared. Well, yeah, there's no atmosphere up there, so you're not going to get the plasma created when they go higher up.
So it's not aliens.
Well,
I think that, yeah. Again.
I don't think there were. But the other thing that bothers me is I believe this was done by Americans. Particularly because that day he said they changed what we were going to do. So I think it's unethical not to have informed them,
Right.
these pilots.
Absolutely.
Not maybe right away, but within a span of time. And second, do they really know now what it is? And then why is it being brought up and not explained?
Right.
So there's some issues to work out, but I am convinced it was this laser-induced plasma strings.
Right. You think that if there's a submarine down there, whoever else is in charge of, the Air Force or those missions, they would know of each other's presence, right? So why they're not explaining that it is, which seems like a very plausible explanation, and I'm sure there's a lot that the militaries have kept from us. So that's something that we're not going to get the answers from. That's very cool and a very interesting theory, which is probably a lot more realistic than aliens, as much as I like to hear that be the case.
Well, we always have to go to the simplest theory, to natural first.
Yeah, yeah, I know. It's the idea of whether aliens have visited Earth, and as much as I'd like to believe that they have, I just feel like it's not like aliens would come down here and just come up to Area 54 and say, okay, we're here, but don't tell anybody, kind of a thing, or Area 51, excuse me.
Do you remember, I'm sure you saw the movie Independence Day.
Yeah.
I love that movie, but I'm also very frightened because those aliens are like insects going from planet to planet,
right,
using up resources. And I just hope if we have encounters, they're not like that.
Yeah, I hope they're friendly.
And even Stephen Hawking, towards the end of his life, said that we should be careful because he thought alien encounters would be with hostile aliens and not friendly aliens.
Yeah, like you mentioned, researching other planets to see if there could be life so that we could terraform it and make it our own planet. In that same respect, there may be far more advanced civilizations of aliens with planets that are much closer to that 5 billion year stars that are much closer, that are looking for planets that have the technology to do so today.
Yeah.
And there's a good chance if they come here, they'd want to do that to us.
And there was a movie, I don't remember the name, but Charlie Sheen was in it. It's about these aliens came here and they were increasing the CO2 emissions to make a hotter world because that's what they needed.
Oh, okay.
And,
yes. Oh my goodness. I just got a flashback to that movie.
Yeah.
Yeah, it was from from the 90s.
Yeah.
Yeah. I forget what it's called, but yes, I totally remember that movie.
Yeah, it was.
He communicates. He picks up a signal through radio frequency, and then yes, that's right.
Yeah, and then he goes to. I think he went to Arecibo, and went somewhere south and started uncovering these things, and then he his life was in jeopardy. But I thought that movie was a little ahead of its time,
Right.
because it was relating climate change, which people still weren't concerned about at that time, but relating it to aliens as being the cause of it.
Right. Very cool. Yeah, I'd be interested to see obviously if other alien life could come to Earth, how much more advanced would they be and how different would they be? Like you said, reptiles with spaceships, very, very cool. Sorry, I'm just taking a look here. So yeah, in that respect, do you think that do we know where the center point of what we think the universe is? And the reason I ask this is if we assume the universe is expanding, and coming back to the evolution and alien life, right? So if we kind of know where the center of the universe is, and these planets that are expanding obviously are forming later than the center planets, they would have a lot more time to evolve, and there'd be a larger chance that there is more intelligent life on those planets. Do we know where the center of the universe is?
There is no center.
There is no center.
It's because here's how to look at it. If you bake raisin bread, so you have the dough and you have the raisins in it. When you start baking, the raisins are pushed by the dough and move, but each raisin is moving away from each raisin. So the idea is that if you went all the way back and made it smaller and smaller, they were all together at that time. Mm-hmm. So I like to say every point is the center of the universe.
Makes sense, because it all came from the same
exactly.
place,
It
right?
came from the same place at that time. So we don't talk about a center, but what you're saying about the formation times of things, those will be dramatically different depending on the local environment of the stars and what's around it, and supernovae that have occurred that have enriched and allowed rocky planets to form. Mm-hmm. Because another problem is that, we have lots of rock on Earth. It's very dense. Even water is dense. The average density of the universe is like 10 to the minus 24th grams per cubic centimeter, hardly anything. And so how did all this get there?
Right.
And it's gravity, and it takes time, but it does happen, obviously. And so some of them could have been triggered earlier than others. And so we have older planets. But the other thing is, when you have the first stars, there's not heavy elements to produce the rocky type planets. It's all gaseous. So it takes a while to build that up. But there could be, definitely are worlds that are much older and could be wiser creatures on it and looking for a new home. Yes.
Yeah. And then I wanted to also talk about rogue planets. And essentially they're just planets that have essentially derailed perhaps from some sort of center. How does a planet become a rogue planet? It's essentially, what is a rogue planet and how does it become one?
Okay. Yeah. So a rogue planet is one that has literally escaped its solar system. It had to be in a solar system to form because it's mutual gravity. It's a condensing cloud of stuff that starts spinning, and then the central part becomes a star. Planets are forming out of a disk that is around it. And so that's how we understand planets. They're not just born out of space. There's just not enough gravity to pull things in and form an isolated planet. So it has to be associated with a star. So it was with a star. And then the other things is stars can pass somewhat close to each other. And in doing so, planets that tend to be farther out, say on the orbit of Uranus and Neptune even, could get enough of a tug and pushed away from their central star.
Okay, that makes sense. And how much of a force needs to be put on an exoplanet to be able to just get jutted out like that?
That's hard to say. It's not just the force itself. It could be the force in time that it's going. So it could be a real rapid one, but usually it's probably a more gentle one, or it could be multiple passes, do things like that.
I see. Okay, cool. So I want to tie back around now to black holes.
Okay.
So when a star dies, it turns into some of this. Some people may already know, but I think it's good to define these before we dive deeper into it. So when a star dies, it turns into a black hole or neutron star, like you said earlier. What would determine whether or not it will become a black hole or a neutron star?
Okay, it's all the mass of the star. So the mass actually of the central core of the star. So as a star evolves, it first fuses hydrogen into helium, and that's what our sun is doing, and that's going on in the core. And then the energy is being released by very energetic light, gamma rays in the core that eventually get moderated as it goes and comes out as visible light by the time it's leaving the surface of the star. And so once one element is exhausted, and we always start with hydrogen because there's a lot of it, if the star is massive enough, it can start fusing through nuclear fusion, fuse the next element that was produced. So that would be helium. And then helium becomes carbon. And then carbon becomes oxygen.
So oxygen keeps going up the periodic.
Keeps going up. And so very massive stars can do this. And it turns out that we're talking about masses, say, 5 times the mass of our sun. So they're pretty hefty stars to start with. But as it does that, it also starts going faster. It burns up things faster because it's so massive. It needs so much energy that it just quickly goes to the next stage.
So the reactions are quicker.
Yeah, and the reactions are also very, very, very sensitive to temperature. And so a very small increase in temperature makes them go really fast, and it burns up more energy. And so as this happens, you get a layer structure for the star. Hydrogen yet that was never fused in the outside, then helium, carbon, oxygen, nitrogen, magnesium, silicon, and then finally you get to lead, and lead is just the most stable nucleus, and you can't break it apart, which would be fission, and get energy out of it, and you can't have them smash together and fuse and produce energy. So you're stuck. And so this massive object has no energy source anymore. And that's, if it then, that core has a mass of, let's say, 3 times the mass of the sun, then when it all comes collapsing, the supernova occurs, the core that remains, that is 3 times the mass of the sun, gravity is still so strong, nothing can stop it. And it just starts to, within a fraction of a second, it's a black hole.
How does that collapsing happen in the first place? What causes that collapsing in the first place?
It's gravity. So it's all pulling in on itself. And it's not generating the energy to stop it, because this is what's always going on with stars. It's a battle between gravity pulling things in and the pressure it can generate through these reactions that create heat and energy, and things collide inside and create pressure outwards. And so there's no way to create that pressure outward anymore. So gravity wins, and it shrinks, and it shrinks into what we call smaller than its Schwarzschild radius. And in doing so, we can't see it anymore. So that's why I call it a black hole. No light can come out of it. No light is trapped inside.
It's always been so hard to wrap my mind around that idea that is it because its gravitational pull is so strong?
Yes, even light can't escape.
And how, because my mind is, you mentioned earlier something interesting about the difference between physical matter versus energy. And so when I think of things not being able to escape it, I can wrap my head around objects,
Right.
being pulled by it. But something like light pulling something in just seems
well, it's light being pulled in by gravity. And but here's the connection. The connection is gravity is this force that can stretch and warp space and time, space-time we call it, which is the four-dimensional fabric of the universe that we exist in. And so what it's like is, the usual demonstration is you have a rubber sheet, a thin rubber sheet, say, and you put a ball in and it dents the ball. So that'd be like the sun. And if you take another ball, a smaller one, and put it around, it'll go around in a circle naturally. Mm-hmm. So the gravity is that curvature of the rubber around that star, and it's telling the other one how to go. Well, now when you get this black hole forming, you have this star and its mass, and it's kind of pulling on that fabric and pulling, and you can imagine the fabric gets really steep.
Right.
And that steepness is saying, okay, nothing could escape. Light can't escape anymore. Right. And because time and space are stretched out so much. So the black hole is somewhere in there, and we call it a singularity, which I tell kids semi-seriously, that's a code word in physics, meaning we don't know what it is.
Yeah. So yeah, it could be, we call it a hole. It could just be a point that's just so small we can't measure it or understand it.
But it still has this larger radius that light can't escape from. So there's a region in space. So if you were traveling in space and approaching a black hole, it's black. How are you going to see it? Well, you would see background stars. And then all of a sudden, as you were getting closer, you'd start to see this void opening, but the stars around it seem to be like bent around.
Warping.
Yeah, warped. And that's all from this intense gravity of that black hole. And so as you approach them, finally, you just see this big void. And by that time, you're probably doomed because you're not going to be able to escape even out there. Right. But that Schwarzschild radius is what's there. You probably saw the pictures of the black hole at the center of our galaxy in an M87 that were down, which were incredible. And it matched exactly what everybody thought. That donut shape is really light. It's really the disk around it because stuff is swirling.
Right. What makes our galaxy look like the way it is the fact that there's a black hole in the center. Is that
that actually probably, that's one of the ideas, is that they're the seeds for galaxies, and it caused that to be that. But the kind of donut shape that it had to the light was was the bending of starlight around in this intense gravity. So.
If an object like a planet or something got too close, physical object, to the black hole, would it essentially like suck it in per se? Like it
would rip it apart.
Would rip it apart.
Yeah, and in fact, one of my former students got an internship at Harvard Smithsonian Observatory last year, and the person she was working with researches galaxies and black holes. Well, she discovered the signature of a star being ripped apart as have these observations and leaving a trail, like forming a donut around it. And she gave a talk last year, January, actually this year, January, at the American Astronomical Society meeting. And it was like this big hit that all the media picked up and stuff, and it was so cool. This is my student doing it.
That's very cool.
So she's in graduate school now, and I'm sure we'll do super well. So yeah, they get ripped up. And then the other thing is, if you were to travel towards a black hole and you got too close, what would happen is you would fall through this Schwarzschild radius because it's sort of an imaginary separation point, a boundary, and you would be just pulled to shreds right away because gravity would be so much stronger on your feet than on your head. It would just pull you into a real thin object and also squeeze you too. So in physics, we have the term called spaghettification. And that's you become like a piece of spaghetti if this happens. However, so it'd be very painful. It'd be just like that. You'd fall in but someone observing you from a safe distance would never see you fall in. You would be hanging above that Schwarzschild radius forever because time is stretched out an infinite amount. Wow. What they observe. So according to you, you fall in, but according to the observer, they still see you there. But the light from you is also stretched out, so you go from visible to infrared to radio. And so you do become unseen again, but we think you'd still be there.
Wow. So I want to talk about high time travel or high speed travel as far as my understanding from sci-fi movies. For example, well, first I want to go to Interstellar first, because in that movie, he falls into a black hole, and essentially he doesn't get ripped to shreds, obviously. Right. But that was my initial thought when I watched it. I'm like, and I guess they're using creative liberties to say we don't know what's on the other point of the point of singularity. So
Well, actually, I think the black hole that he went into was a rotating one, and the singularity is not a point, it's a ring. And so you can actually, if you had a spaceship strong enough to resist the gravitational pull, you could actually go through it and not be destroyed, is the idea. So it's a different, slightly different type of black hole, but still is a black hole. So I have a feeling that's what it was, because the technical advisor was Kip Thorne, who was a professor at Caltech, and so everything was all by the books. The only thing was, he's seeing, like, the
bookshelf.
Yeah, the bookshelf, and that was the kind of the hokey thing where they had some liberties at. But most of the other stuff was good physics.
Well, because you mentioned it does bend space and time.
Yeah.
So is there a way is that the idea behind harnessing space and time in order to travel close to the speed of light, or to create wormholes?
Wormholes, yeah. So a wormhole is that idea that we can basically bend space and time, and when we do it, it connects. It just doesn't, you don't rip it, you connect it to some other place. And so you literally have two places, and you stretch open space-time and then have that tunnel or bridge. It's called an Einstein-Podolsky bridge to this other point, and which you could then travel through. Okay, but you would travel, million light years just like that
instantaneously.
So Stargate, I don't know if you ever saw the series Stargate or the original movie.
Yeah.
And that was the idea, which I thought was really great. And the problem is, we think that would work, but we don't have the energy to do that, or the way of holding open that tunnel in space-time. There's some particles hypothesized that we would need, but we haven't even observed them, so that's still fantasy. But it's we kind of know how it works, but we don't know how to actually engineer it.
Right.
Yeah.
My movie experience with that was the movie Event Horizon, and I saw that when I was a kid, and that freaked me out.
Yeah.
Definitely took it to a darker place. It's more horror sci-fi, but so essentially that wouldn't even be light travel. It would be instantaneous, which is different than trying to create enough speed to travel at the speed of light.
Right.
Which,
because that traveling at the speed of light can require a lot of energy.
Right.
And you can't really take all of the matter to create the energy with you. And if you scoop it up, it's got to accelerate. So there's a lot of problems. But there's somebody had an idea. It's an engine. I don't really believe how it works, but it's supposedly with light bouncing around and it can do propulsion. But that again is would take a very, very long time to get up to speeds of light.
Right.
Although right now, Voyager 1 and 2 have left the solar system, so the farthest humans have ever sent anything out. And they are moving at, relative to us, I think around 1/10 of the speed of light.
Oh, wow.
So it's, it's been since 77. So little by little they get boosts and it can.
Through by gravitational pull from other planets.
From other things. Yeah, we used it from the big planets to get out and actually escape our solar system. So it's kind of cool.
That's awesome. Well, that'll help us. Hopefully, one of the two, either light speed. It'll only take us 11 years to get to our nearest planet when we need to terraform it.
Yeah.
And so the Milky Way and the Andromeda Galaxy, which is our closest galaxy, I read they have a pull with one another between the two.
Oh yeah.
And what can that lead to them like fusing together, or what is that the idea?
We're going to collide with Andromeda before our sun actually becomes a red giant.
Oh wow!
So we have another thing, but
so we would need to go outside of those. We need to go even farther.
But it's not so worrisome because we're fairly far out. We're about 30,000 light years from the center of our galaxy. It's going to be the two centers of the galaxy that are going to really want to orbit each other when this happens. But planets could be dislodged from stars. There may be a lot of stuff. There'd be more chances of being struck by meteors and things. So it still could be very dangerous. But we're going to merge with Andromeda. And we have evidence of this happening in the past with galaxies. We still see them in the process of doing that.
And I read about, again, this has something to do with gravitational waves, does it creates gravitational waves?
Yeah, they'll create gravitational waves.
So what are gravitational waves? And
well, simply put, it's the space-time is this fabric, and so waves. The way you alter space-time is through mass. And so if you have very massive objects like galaxies colliding, or two black holes or two neutron stars even, and probably in a while we're going to be able to measure them from even smaller, less massive objects. But those events of them spiraling on really fast and colliding create ripples, like throwing a rock in a pond. And those ripples travel out. They're really small, but they travel outward. And so those are the gravitational waves that we now can observe, which, again, when I was an undergraduate, actually at Northwestern, a high school student actually at that Northwestern program, we went to Argonne National Lab, and there under us in a stairwell was this big metal cylinder, and that was the first experiment by Weber to measure gravitational waves. Now, he never found any. And now we have two identical facilities, one in Washington, one in Louisiana, that are big L-shaped arms where these laser beams go, LIGO, and they bounce back. And if there's a gravitational wave, it's going to make matter move ever so slightly, and we're able to pick that up. It's incredible technology to get to that, and it's getting more and more sensitive as well. So,
and what is there anything that we can answer with knowing the energy? Like what can it help us figure out?
Well, they're really small. The energy in there is not very small. When you add up over all space, it's large but small. We probably can't do anything useful out of it. But on the other hand, if say there were two neutron stars within 10 light years from us, okay, and if they were to collide and there were these ripples, we would be like standing in an ocean and waves go by. We would be pulled and swayed and squeezed. And if they were strong enough, that would mean your molecules would move far enough where they're not going to be bound anymore, and your whole biological system can break down.
Wow.
So there's a danger there.
Yes, yeah. It's so.
It's a dangerous universe.
Yeah, absolutely. Going back to the black holes, there's a couple things. One of my students wanted to ask about white holes and what they are.
Yeah, we don't have really evidence for white holes. It's still an idea, but a white hole was originally conceived as the end of a black hole. So remember, you have that tunnel that goes to another place in space. Well, there could have been where the star collapses that really created a tunnel, and the energy's coming out somewhere else. And that would be just energy coming out in a point in space. So we call it a white hole.
Oh, okay.
Energy coming out. We've never really observed a phenomenon like that. Usually it's a star, we say, or something like that. So they've never been confirmed, but they haven't also been negated as an idea.
So it's just energy coming through to the other side of that that wormhole, quote unquote.
Yeah, so that would be a connection there between the black hole and the white hole of things. But unfortunately, every now and then, I think it might have been 2 years ago, there was could this be a white hole? And then I don't remember, but it wasn't. It was associated with
something else. If there was, that could give us answers as to whether or not the idea of a wormhole would be possible, right?
Yeah.
Okay, very cool. And then I don't know anything about it. I just heard it in passing, something about the Event Horizon Telescope. Are you familiar with that?
Yeah.
With that, what is the telescope, and how is it used to? All I know is that it took pictures of the same black hole from different spots.
Well, yeah. What it is it's using basically radio waves, which are long wavelength. Like radio telescopes on Earth, they're very big dishes out in, say, Arizona or the Atacama Desert in Chile. So to get enough definition to see this, well, they were pretty big. It's probably the first one imaged was maybe 10 times bigger than our solar system. It's a big black hole.
Yeah, wow.
And so, but still, it's so far away to be able to image that with these radio waves. You need a really big dish to collect the radio waves. Oh, okay. So what they did was use the whole Earth and then different observatories on the Earth with radio telescopes to pick up the signal. But then you had to coordinate that all those signals are coming in at the same time. And that's where one of the Nobel Prizes was given for really just figuring out how to do the calculations to make sure when those waves come in that you're getting all the same wave at every instant, so you really can't image it.
Right.
And so that would have been the Event Horizon. It's basically using the whole Earth essentially as a size of a telescope.
And using ways to recreate a picture, essentially.
Yeah, to recreate the information from it, yeah.
Wow, that's very cool. And the quasars are just. Can we dive into quasars for a second? Just talking about what they are. I know that they have to do with the gas or some sort of gas being eaten by a black hole or something. But
okay, so yeah, quasars were another interesting thing that at first we didn't know because they were objects that were very dim in visible light, but very bright in radio waves and producing all this energy in radio waves. And like, what's doing it? But we don't see any big object or something. And so it was a mystery for years. And then finally it evolved that, they're really galaxies. And there's a supermassive black hole sitting in the middle of this galaxy that's devouring other stars and things around it. And as the matter swirls around in a disk around it, the pressure on that matter gets so great that it sometimes can escape by going perpendicular to the disk, up and down. And those create jets of matter being projected outward near the speed of light. And those particles, they're usually charged, wiggle in the magnetic field that the galaxy has, and that wiggling produces the radio waves. and those radio waves then. So what's really cool is I have pictures of where you're looking at a galaxy and the picture's like visible is that big. And then you superimpose the radio waves that we see, and they're like this big coming out. So it's really a lot coming from that. And so then the quasar, that would be a quasar. And then sometimes we see two of these lobes because of the matter coming out one side and the other. Sometimes we only see one because it's obscured by all the other stuff. It's just not, one's a little bit more pointed towards us. And so quasars are really what we call active galactic nuclei, which means they're the centers of galaxies but have these supermassive black holes that are currently devouring stuff. If they're not, then you don't have that disk, you don't have the jets produced and that. So it has to be that the region around it has enough stars, planets to be eaten by that black hole.
So right now that's currently happening in the Milky Way, right? We don't, the center is just slowly sucking in or just eating the center, eating the stars that are around it.
Yeah.
Just eat, wow. Can there be, at the center of every galaxy, does there have to be a supermassive black hole? What's the difference between a regular black hole and a supermassive black hole?
The mass and size is the difference. When we get to supermassive ones, so a regular black hole is, say, 3-5 times the mass of the sun. Supermassive ones are going to be like maybe 20 million times.
Oh, wow.
So a lot bigger.
Wow.
And so the idea was that, were they around and that's what caused galaxies to form? We don't know. Do all galaxies have them? We think so, but there are some we don't seem to see any evidence for. So it's an open question yet.
How can there be such a big difference in size between two black holes? Like, I realize that there's big differences in sizes between stars, and that can essentially be what creates that.
It's going to be that in the center of the galaxy is stars are much closer to each other. It's much more compact. And so if some stars, evolved to black holes and they merged, and then as that got bigger, anything near it gets, if it gets too close or is too close in orbits, is shredded, and then that energy feeds the black hole. It grows and it grows and it grows. And so that's how we think they could have formed. There probably weren't supermassive black holes produced early on in the universe. That's just way too massive to produce.
So a supermassive black hole is not necessarily caused by one planet.
No.
My one star, excuse me. Okay.
It's going to be millions of stars if it's going to be that big.
Oh, wow. Okay. So
and to give you an idea, we have things orbiting the galaxy, probably all galaxies. They're called globular clusters. And they're kind of early formations as the galaxy is forming. And they're usually very spherical, dense. And you do telescope. You're going to have to come out to our observatory and you can bring the kids and see these things.
Absolutely.
They're cool. But the average distance between stars there is much, much less than in our region of our galaxy. So, for example, the nearest star is 4 light years away from us. If we were in one of these globular clusters, 4 light years sphere around us would have probably about 10,000 stars.
Oh, wow. Okay.
Yeah, so there's a lot more. And I like to tell kids, and then what's going to be different? Well, would we ever have night? Would there be enough light coming from the stars? It's like we just have shades of light that would go on and stuff.
You wouldn't need city lights anymore.
That would be nice. But then again, you would never know about what was out there if you could never see it. So that would be a sad aspect
true.
too.
Right, that's very true. It'd be so bright, it'd be hard to see past them.
Yeah. So anyway, but there's just that different density, and that's what you're experiencing as you go towards the nucleus of the galaxy.
So if our Milky Way keeps going as it does, like devouring planets and then eventually the entire galaxy, would it just be one huge black hole essentially, like it would, as it grows in size?
I don't think we think it'll any black hole would consume the whole galaxy. I think it would because that density is going to change, and finally there's going to be stuff out there. Because black holes just don't go around sucking in everything. They have to be things that pass by and fall into its influence gravitationally.
Right.
So it's, I think I would safely predict that no galaxy would ever be completely eaten up.
Right. Because on the outskirts where the gravitational pull is weaker, it would never just get to that point.
Yeah.
Right.
Yeah.
So there's no observed or anything close to what we would see as like a close to dying galaxy in that sense.
Well, we have galaxies, but there's no very low rate of star formation. Mm-hmm. Galaxies are really containers for stars, and they're recyclers. They recycle all these elements stars are producing and produce other stars and planets. So you just probably wouldn't have that happen, I think.
So you talked about them creating new stars. Is that how nebulas are formed, or?
Well, there's two types of nebulas. Well, there's several, but two basic ones. One is ones that are just regions of gas and dust inside the galaxy. So that was produced earlier on, and in the Big Bang, and these clouds, called molecular clouds, and then a galaxy would form out of part of it. And so that is one term we use for nebula. So we have regions around Orion, for example. There's a lot of this gas that new stars are forming out of, and we can see them forming and see the gas and to get all these beautiful pictures. I think there's some of the most beautiful pictures are of nebulas. But then there's another one, which are called planetary nebulas, which have nothing to do with planets. And by the way, the name is that in astronomy, once you name something, you never change it. Astronomers are curmudgeons. They just, but you have to do that. So historically, you know what everything is.
Sure.
Anyway, planetary nebulas are stars like the sun, sort of low mass stars that eventually will puff up, become a red giant, and then kind of push out slowly the outer layers. And it's those outer layers going off into space that are still excited by light from the star. And so they have colors, and they're telling you elements that are present, but they have different shapes. And sometimes binaries do that, and you get different shapes. So the planetary nebulae are just the most beautiful aspects of astronomy, I think, too.
And would that create... is that creating new planets or new stars?
It's enriching what we call the interstellar medium, the stuff between stars, so that, yes, new planets and stars can form.
Wow, so this is constant cycling,
but
over a very, very long period of time.
Very long period. And then supernovas do the same thing, but much more material and much stronger velocities associated with the particles. So there's actually a wind.
These are the much larger planets that turn into supernovas, or
the stars that turn into supernovas,
which eventually turn into black holes, or
some of them can if they have enough mass. Yeah,
so a supernova could turn into a neutron star or a black hole. It's defined as not a supermassive black hole. Sorry. So what's the term we just used? Sorry, I'm getting them mixed
It's going to be just a black hole would come from. If the mass of the star after it's evolved...
Supernova, excuse me,
Supernovas, 3 to 5, greater than 3 times the mass of the sun.
And then what would be the categorization size smaller than a supernova?
We have novas, but they're totally different.
Okay.
Novas are binaries where one of the star gets enough matter accreted on it, and it fuses for a while and becomes much brighter.
I see. Or categorizations of star sizes, what would those be as far as their names are concerned?
Oh, okay. We have actually we use Roman numerals to denote them.
Oh, that's what those numerals are after the name of the star. Okay.
Yeah. So a 1 is going to be the largest, and so for example, Betelgeuse is a 1, and it's called the luminosity class. Then you work your way down, so you have supergiants, you have bright giants, you have subgiants, and then finally you get to what were called dwarf stars, and that's where the sun is. But we don't like calling our sun a dwarf. So it's called main sequence because 90% of all stars follow that plot on this thing called an HR diagram, but they're related. So it's masses can go from about the lowest mass is 0.08 solar masses, and then the upper end would be masses maybe.
Sorry, how big is that compared to say our sun? The sun?
0.08 is really small. That's the mass of a little bit more massive than Jupiter.
Okay.
So to give you an idea, so Jupiter's, if it had been a little bit more massive, could have been a star. We'd have a binary system, which would have been cool. But the upper end, you can have stars, say 50 to maybe 100 times the mass of the sun that are along this main sequence. And we're one of those. And then you keep going, and there are the white dwarfs are down below, but those already evolved. Those are the lowest mass ones. The other thing associated with that people don't realize is that most of the stars, I mean, most like, I'd say it's probably over 90% of all stars are less massive than the sun. So we call them red dwarfs. And red dwarfs are by far the most populous stars.
Oh.
And so now one of the things TESS is trying to do is to look for red dwarfs and to look for planets around them. And there was one discovered a few years ago, a TRAPPIST, and there was a lot of excitement that we thought it was Earth-like and would be just in this Goldilocks region, and maybe that would be it. And then astronomers were observing one day, and there's this flare from the star, even though it's a small star. This flare, and the planet was like cinder.
Wow!
I mean, it was really so. And the problem is with these red dwarfs, they spend a long time in their terrible teens. And so they're constantly having flares and stuff. And these stars, those stars live, our star lives 10 billion years. They live on the order of trillions of years. I mean, very long.
Oh, wow. Because they're not, their chemical reactions, like you said, aren't
not as fast. Yeah,
right.
They're slower. So but they have other problems, which are they tend to have flares and things that, why, I don't know. I don't know why they.
Are solar flares a danger to us?
Yeah.
So, what kind of danger are we talking, and how in the past, how has that affected
to us in particular is now because of our technology. So when there is something called a coronal mass ejection, which there was one that supposedly was hitting us this past weekend, that it's hot plasma is ejected by the sun. And this is going to be when there's a lot of sunspot activity, as we're approaching a maximum now of sunspots. So it puts out thousands of tons of matter. And if we're in line of it as it travels out, it's kind of got its own magnetic field. It's kind of like held together. And then it hits us. Our magnetic field is a shield, protects us from it, can deflect it, but not entirely all the time. So some things get through and they spiral in our magnetic field, hit the atmosphere, and they create northern lights and southern lights. So we get increased auroras, and if it's energetic particles coming in, those auroras can stretch further down the globe and go to lower latitudes. And the ones that hit, I saw some pictures were Missouri, which is getting pretty close to here.
Yeah.
So there is, so now technologically, if that happens, they will burn out circuits and satellites.
Like an electromagnetic pulse, essentially.
Yeah, exactly.
Yeah.
That's exactly what it is. And so one of the things that can be done is the satellites can actually move a little closer, more within our magnetic field to be shielded. They also can be powered down to just minimal power to get a signal to power back up.
So we can anticipate them.
Oh, yeah. We
have plenty of time.
Yeah, we have SOHO. It's an observatory that moves around the sun, and we can really monitor to the sun. So we know if one's coming. And if once it's ejected, it's going to take probably a couple of days to reach us. So there's time to react. But it's mostly our technology that's in danger now of it.
And they can't affect our climate in any significant way.
Well, it does in a way because it's more energy deposited. This were happening. It would keep heating up the oceans because we're mostly water. So yes, but we don't think it's any major component. However, that having been said, we have historical evidence that in the 1685, I think is when it started. That was the little ice age in Europe where the rivers froze in Europe and the summers were very short. And that went on for almost 50 years. And that we know was correlated with almost the absence of sunspots. So the sun wasn't very active then. It wasn't ejecting things. So it's a kind of interesting comparison. The sun has been a bit more active the last cycle. The cycle is 11 years. So,
sorry, what year did you say that activity happened?
I think it's 1685.
1685, okay.
And that's the lack of activity.
Right.
It led to the little ice age. So that's all well documented. And you look at the number of sunspots, which has kind of been kept since the time of Galileo, who discovered them, that it was really at a low number throughout that 50-year period, which would have been about 4 cycles. And normally they go up and down every 11 years and quite dramatically the number of sunspots that we're seeing. So yeah, so it's hard to tell what's going on.
Right, yeah. And going back, you'd mentioned climate change earlier and our role in climate change as humans, as how we've contributed to it, but then trying to quantify that amount when we've got things like that, or the Milankovitch cycle with the tilt of the Earth and the fact that we go through these periodic ice ages because of the tilt and the way the rotation of the Earth around the sun, and how just the tilt and the way it wobbles can affect climate. It's hard to quantify. Right. Our effect on it. It's definitely there, but the idea is how much, Right.
Yeah. And it's extremely difficult. And the other thing though is that areas of science now are moving quite differently. Instead of having a hypothesis and perform an experiment, we can't experiment and do this. We just have to look at data. So we're going into the realm of data science. And data science is giving you huge databases, and you look for trends, you look for connections. That's not giving, and then they make models out of that, but it's not the same as creating a model from an underlying physical understanding and building it up from
it's a bit like just studies in general as well, like observational studies in science that are kind of like you can make these observational studies for even in I think human health, diet, those kinds of studies are observational in that sense, and it's very hard to do these controlled experiments.
Right.
So as much as we think we're right in determining some factors, it's correlation, right?
Yeah.
At the end of the day.
Well, I like to warn all my students that data is not knowledge. Knowledge is not understanding, and understanding is not wisdom. So you have to be able to sort them out. And just because you have all that data doesn't mean you're wise as a result from it. So
that's hard to do. It's hard. Yeah. It's hard to say that this is pointing to this direction, and then towards this answer, and then I run this other study or take this data, and it also goes towards the same answer. But also having that in the back of your mind, knowing that might still not be the case.
Right.
Yeah.
Right.
And always questioning whether or not what the truth is. Yeah. It's hard to do that, especially if you're one of the scientists who's invested their lives and years into these studies. Yeah. Because the ego plays a role in that as well, right?
Right. I can tell you just a short story. I'm an editor for a journal, and the chief editor, who's in Poland, contacted me and wanted me to review a paper that already had 2 reviews. One said to publish the article. The other was extremely critical and very vehemently critical of the paper. So I said, sure, I'll take a look at it. Well, it was written by a astronomer, actually planetary scientist, who worked with atmospheres of stars and planets from first principles and trying to understand them. And so he wrote this as a way of looking at climate change in terms of building up the model from the ground up, not just from the data. And he had published like 50, 100 papers, something in his area. So very successful. Things made sense. And then I read the reviews, and it was the review against him, and just totally didn't even seem to comprehend his approach to it. Well, then I researched the guy who was that reviewer, and he was a member of the International Panel on Climate Control. So he has a vested interest too in there.
Not just egos, but vested interests. Yeah.
And absolutely. So he's a data scientist, and the other guy was what I would call a physicist. And so to me, I saw the difference there. So I wrote up my review and gave it to Paulina, and I don't know if it was ever published. I didn't look it up, and she didn't tell me, but it was an eye-opening case for me.
Yeah, we humans, we get in the way of the truth. Our own ego gets in the way of the truth.
Yeah.
Yeah. And it's, since so much research is funded, by outside, from donors to, it's wherever you have to question where that money comes from at the end of the day, because a lot of times, we've seen that countless times with the pharmaceutical industry, with the food industry, for the fats being demonized, in the 50s or in the 60s, and which brought the rise of the sugar industry, and now we're slowly learning, hey, sugar is probably not the best thing for you, So fat was scooped out of yogurt because fat kills you, and it was replaced with sugar to keep the taste, and fast forward, and we have an obesity epidemic.
Yep. No, that's yeah.
So, I was going to ask about the star, the size. You said they were quantified with Roman numerals, the one being the largest, like Betelgeuse. How much larger in size is Betelgeuse compared to, like, say, our sun in an orbit?
Okay, so I would say the following comparison. If you have our sun, you kind of imagine how big it is. If you put Betelgeuse where the sun is, it would stretch out to the orbit of Jupiter, maybe a little past Jupiter. So that would be, we'd all be inside the star. So that's a really big star. Some of the biggest stars we have found would stretch out past the orbit of Saturn.
Whoa.
So Saturn is 10 times farther from the sun than we are. So you can imagine how big those stars are.
That's it's for me, it's a bit like time. Time is such a large scale. When we look at it in terms of like where humans have been, the little blip that we're on, it's not even a blip of a blip of a blip. It's like nothing.
Yeah.
So for me, sometimes it's hard to just wrap my head around that amount of time, or the sheer quantity of size of something,
right,
or something the size of something as big as the universe.
Yeah. So I think we always have to, I like comparisons always, then I can kind of get a little bit of a feel for it.
But even then, it's like, so the size of planets is derived by the intensity of the light. Is that right?
It's going to be, again, you mean stars?
Stars, excuse me. Sorry.
Will be their mass.
Their mass.
And then the mass, then, which is really intrinsically when it was formed, how much matter came together. And then the cases like Betelgeuse are so large because it's started to evolve and it swelled up and became this super giant.
But how can we tell how big these planets are? Or stars, excuse me.
Betelgeuse is actually big enough and close enough where we can do speckle interferometry, and we can actually measure the size of it, which is incredible.
Oh, wow, okay.
So that one we know pretty well. The others, we do a relationship on the brightness of the star. Compare them. Yeah.
When I was in high school, in the late 90s, that's, how I was taught and that was our only frame of reference for detecting the size of a star.
Yeah.
So now we can be a lot more accurate with.
Yeah, because we have some stars that we can actually we have measured the size, and then and as we've gotten better instruments, better telescopes and cameras, some of the stars are not just points of light, and so they actually are a disk, and we can start to try to actually measure that as well when we know how far they are, and we can calculate it.
So based on this new technology or newer technology, how accurate are we as far as detecting the size of a star compared to the intensity of its light? Like how accurate were we, and have we been able to become more accurate detecting the size of a planet from a star? Because
I think we were actually pretty much right on.
Oh, wow, okay.
And then there's theoretical understanding that backs that up, and that's actually how we're able to predict the other ones. But I think we're fairly confident we've been right on with that.
That's very cool. Is there any other topics that you think would be cool to discuss? I've kind of gone through all of my kind of questions that I've wanted to ask, but one that I'm really curious about now is a few years ago I had a student, and what I do, this becomes their undergraduate thesis. I find a research topic, and then I guide them along in analysis, and then they have to write up a thesis. So I had gotten some data from Kepler, and I thought, well, let's look at this. But the star was a fairly well-known star, UZ Lyra, which means it's a variable star in the constellation Lyra the Harp. So it's visible now if you were to go outside. Well, you could almost see it with your naked eye too. So we were looking at that data, and so I had them do one type of analysis, and what emerged from that was that there was something tugging on these two stars. All right, and so if it were tugging on stars, I mean, just a tiny, tiny bit, but if it was tugging on it, it had to be like, if you want to lift up a heavy stone, pry it off the earth, you use a long metal rod and push down at the end. So you need a long lever arm is what it's called. So that meant whatever it was had to be far away from it to get that enough to leverage and to influence the two stars. And then what I did was, but it was there. It was definitely there, and it wasn't ever seen because no one had looked at the Kepler data. In fact, I found one paper where he had looked and had some variation, but stopped, and he hadn't put in all the Kepler data, which we were doing. And so it was very refined analysis, and that showed there was a planet about the mass of Neptune orbiting this binary star. So that got my interest in planets around binary stars. They're called circumbinary exoplanets. And it's a hot topic in astronomy now. So we found one, and I just thought it was really good. And the student was exceptional at doing very detailed work, and a little monotonous, but that's how science is at points. Sure.
But I thought he did an excellent job. So I was wondering if we could find other ones, and how many are out there, because we used to think there couldn't be planets around binary stars.
Why is that?
Because the stars moving around, their gravity would disrupt in orbit and get like a rogue star you asked about going off. So the idea is, well, how's it going to, well, there's two types. One is an S, which means it's really close to one of the stars. So it's really held mostly by that one.
I see.
And then the other is called a P. It's the pair of stars. It's so it's orbiting like the center of both of those stars. So it's far out there. So the first one we had discovered was a P type. And so I've been curious that, and then last year, students I had, we found in test data a signal of a binary with two planets around it, which there's only been one other observed. So I have to finish I have to do the statistics on it to show that, yeah, there really is something there. And then we can claim it. And then it has to be observed again to be really
Would that be peer reviewed essentially, or observed? Yeah.
Yeah, peer reviewed for the article, and then has to be observed to say it's actually there. It's a candidate until it's got some other observations of it.
Is there a long waiting process? Since there's how does that work? Yeah.
It could be infinitely long.
Yeah.
It depends because a space telescope isn't going to go look at something like that.
Right.
If it's in their campaign of stars they're observing, then you might have the data, then you can use it. So that's what we would hope for. And this was already in test data, so we would hope that tests will have a follow-up of it again, and we can get more data, see if it's still there, and then maybe, I don't think ground-based observations will work, but there might be larger telescopes than what we have that could do ground-based to see if they see the same signal.
And when you yourself want to, obviously you need an advanced telescope to do that type of research. So how often are you using, say, like an at-home telescope to do any work? Is that even possible?
Yeah, when we first started, we were doing surveys looking for exoplanets. So we took a image of the sky through an 11-inch telescope, it's a good size. I bought it through this grant, and it was about probably about $8,000 at that time. And so, and the telescope's just a small component. The camera is like another $5,000 to $10,000. The drive for it to track the stars and keep, and then the associated drive. So you're probably looking, by the time you're done, you're $20,000 for it.
So you've got to set a point so that it can track it.
Yeah, it can track it. So we were doing that every night, and we were in Colorado, so it's very dark sky. We're doing that every night for like 35 nights, and just the same way. And then we would analyze the stars in there. So we'd have about 2,000 to 3,000 stars in every image. So I spent countless nights going through all those stars, taking the data over 34 nights. And of course, we had it computerized where we got the data, we put it in a database. But I would then visually, I wasn't using any AI at the time, visually pull them up and say, okay, is there a signal here? And something you said earlier about how we have something vested. A lot of times it was like, I want to see a signal there. I want to see a signal.
Right.
But I found 7 candidates, one of which we've observed and we have seen it travel. So that's probably really a discovery level. But it was hard. If we'd had a bigger telescope, it would be better. So now we have a 16-inch telescope. It's much better, and it's in Throckmorton, Texas, so about 4 hours away. And pretty dark sky there, so we're getting actually very good data. And we have a new technology camera, so we're reducing the noise and the signal, so it's coming pretty good. And we already found one following up on test objects. We found one where they want to know exactly when's the midpoint of the planet going in front of the stars. So astronomers are really big on measuring time. I mean, that's probably the whole history of time has come from astronomy. Mm-hmm. And so we pinned that down, and then we found that, well, there wasn't just one signal of a planet. Inside that signal, there's another signal, which to me says there's a second planet in what we call resonance, that if this is the sun, the star, one planet goes around faster, the other one goes. So every time this one makes 2 loops, this one makes 1 only.
Right.
And so they happen to be the same place, same time. So we're finding things like that, which is always exciting. And then you got to verify it, which is the hard part. Once you discover it, you got to back it up. So you can use like a 16-inch telescope. I've always had the dream that we could get a 24-inch telescope. Mm-hmm. That's, probably $100,000 for just the scope, or maybe, probably $125,000 now. And that would be nice, but I don't think we're going to get that.
It's funny you mentioned the being interested in time and using that as a way to conduct the science of measuring the stars and how they travel. And that's been done for thousands of years. The fact that in South America they would track their entire calendar, their season by the stars,
right.
which is crazy that back then,
right.
and where we are now and how far we've come, being able to do that. It's been going on since as far back as South America. I'm not sure I'm sure the Egyptians.
Yeah, the Egyptians. Yeah, I actually had a student this summer. I teach a 3-week astronomy course for University of Dallas students in North Carolina. It's a bit darker sky, and it's nicer environment. And so one of my students actually went to Göbekli Tepe, which is the site in Turkey, which is, we think, the oldest kind of astronomical site. So much older than Stonehenge. And there's pillars, but they have carvings on it. So he wanted to see it. And I was like, whoa. And he also really thinks we've been visited by aliens. And I was just very impressed. He traveled himself out to this site. And, so he was able to tell me about it. And I was like, wow, I want to do this. And so he wants to visit some other sites around the world and just take it in.
Yeah, I'd be curious to know what those ancient civilizations knew about, I don't know if any past civilization was as advanced or more advanced than ours. I'm pretty sure we're at where we're at now. But it'd be interesting to know how they got, how the pyramids were built. We still don't know how the pyramids were built. So if we don't know that, if we can't answer that, then there may be lots of things that, even though it might have seemed more crude technology, that they knew things that we don't know today.
And did you know the pyramids are reflecting Orion?
Oh no, I didn't.
Yeah, the three in Giza, the stars in Orion's belt are not all the same brightness, and so the pyramids are not, and the stars are not in a straight line also, and the pyramids are not in a straight line. And then there are older pyramids that can be correlated with Betelgeuse and Rigel and Saiph and Bellatrix.
So from a bird's eye view, it has the same...
Yes, a bird's eye view.
That's nuts.
Yeah, it's nuts. And how did they correlate it? And how did they build this?
Right, and to measuring the distances between one pyramid and the other, and having some sort of an idea of the relative sizes of them to be able to build them. Right. That's crazy.
So then it makes you think, are there aliens?
Yeah, seriously. It's like they'd have to get like a bird's eye view too to make sure everything's panning out as they're building it.
Yeah. And so many things have this bird's eye view of that ancients did, and how did they ever get it?
That high? Right?
Yeah. So I think we have a lot more to discover about their knowledge.
Yeah. Well, if you find a livable exoplanet, and let me know so we can make contact with them.
I would wish. I would wish at times that I'd have a signal. Unfortunately, what we work with, we wouldn't get it. We probably were looking at radio wave signals or stuff. And,
right.
But I wish we had some signal. One little thing about it that's kind of interesting is that we used to say, we had radio waves, broadcasting antennas, and so those waves just travel out. So a planet, now, let's see, 50, 60 light years away would be picking up I Love Lucy and all these TV broadcasts. But so we would think other civilizations would have done that, and we should be picking up these radio waves.
Right.
But then you have to look at what happened to us. We don't really broadcast that anymore. We have microwaves, which then have limited range.
Right.
And we have cable, and we're not broadcasting as much out into space, and
That's
they
true.
probably aren't as well. So then it's hard to detect that.
Right. If they're an advanced civilization, they're not going to be using that.
Yeah.
Yeah. Unless they happen to be right where we were 20 years ago.
Yeah.
That's interesting. What's your favorite sci-fi movie, or your favorite couple sci-fi movies?
Okay. Arrival.
That was a great movie.
I like Arrival because it wasn't so much about the aliens per se.
And I still haven't watched the movie all the way through. It's my wife watched it a couple of times, but I watched like a big part of the end and the beginning. But sorry, go ahead.
Yeah. So Arrival is one and a current one. I guess quite honestly, my all-time favorite was The Day the Earth Stood Still, the original one with Michael Rennie and the robot, and it's where this alien comes to tell us to quit fighting and stop nuclear weapons.
And the remake was pretty. There was a remake.
Yeah, there was a remake, but I like the original.
Okay,
and then another one, which is an old one, was Forbidden Planet. I don't know if you ever saw it.
No.
You got to watch it.
Yeah.
It's for its time. The special effects are incredible, and it's basically the Tempest set in space, where these humans go because there's a human spacecraft that had crash landed years earlier. They want to see if there's anybody left there, and there is a guy and his daughter. Morbius is the scientist and his beautiful daughter, and they're just like, how did you survive all this and things? But then he has a robot that was like Robbie the robot, was actually what it was originally. And then there's something on the planet there that ends up starting to kill the humans that have just arrived, and they can't see it except when they have a force field and they see this outline of this thing. Well, it turns out that this guy realizes there was an ancient civilization there called the Kral, and they had learned how to transform or transfer matter at will. And they had these huge machines. They look in it and it's just like, 1,000 levels underground, and these going on that would produce the energy to do this, but they learned how to control it. Except they didn't realize they had evolved from a lower being, and they had this id, this ancient animal part of them that now could be powerful and could take advantage of that system.
Oh, cool.
And that, in a sense, was like their evilness, their bad side. And that's what's loose on the planet. And it becomes part of him, that he can control it, and it's his id that is coming out and just killing these guys.
That's very creative. That's a really creative story.
Really,
it's kind of a parallel of, it's probably an allegory to humanity, maybe probably.
Yeah,
well.
yeah. So I really like that. And then there's some newer ones.
You were saying, sorry, Arrival, before I interrupted you earlier when you were saying Arrival, you said what you liked particularly about it, and I didn't let you finish, but I'm assuming it's because of like the realness that it has. It feels like what would really happen if we knew that aliens would come down. Yeah,
and the aliens are really cool, and the whole writing and the whole idea that you're being transferred in time by the writing and the language. It's just, and I actually wanted to read the book that it's based on.
Oh, I didn't know it was based off a book. Okay.
Yeah, it's really amazing concept. So I've got to watch. I took one of my classes to watch it as a field trip. We're gonna watch Oppenheimer in a couple weeks.
Have you seen it yet?
No,
I haven't either. Yeah.
So I'm probably gonna watch it next weekend, and then a couple weeks after that, show it to the class, stream it to them, and other sci-fi movies. And I mentioned Independence Day. That's just kind of a fun one.
Yeah, for sure.
War of the Worlds.
Oh yeah.
But I like the original.
Yeah,
the original.
The original one, I definitely like better too than the remake. The remake's, Tom Cruise. It's Hollywood,
yeah,
but
exactly.
still good. 2001: A Space Odyssey is a movie I always come back to because of when it was made, how long ago it was made, and how ahead of its time from a visual standpoint it was, and how it was able to be pretty accurate, from all facets of it.
Yeah, I remember going to the theater with friends to watch that.
Yeah,
it was like,
awesome.
Wow, this was just so ahead of its time. So I generally like a lot of the classics, and then I watch some newer ones, but they're not really mainstream popular. As I watch a lot of Norwegian movies.
Yeah, if you send me some links, because I'm always into finding some cool sci-fi ones. And unfortunately, most of the sci-fi that I watch too is like dystopian future sci-fi stuff. So.
Well, here's what's happened now. If you stop and think, we've moved away from movies about aliens. It's not like Alien the movie or Prometheus or stuff like that.
Right.
And now it's all really us, and it's dystopian. We're the ones that are wrecking the environment, or we're doing this and that, and so it's the focus has changed from out there coming and invading us to ourselves invading what we
destroying ourselves.
Yeah.
Favorite quote from probably my favorite sci-fi movie, which is Terminator 2. It's in our nature to destroy ourselves, and obviously it's that's a quote that's been used before, but that's definitely one of those, a perfect example of a movie where we destroy ourselves. Absolutely.
Go ahead.
With especially with AI coming out too. That movie in particular has got me thinking about the implications of that, and and there's very smart people on the foreground of that, who are scared of what AI might bring.
Yeah, I know. I am too.
Yeah, I think a lot of people are more scared of the economic problems that it might cause for people who might not need to work anymore. It'll put people out of jobs, and we may not have the ability to kind of catch up with that. It's because it's moving at such a fast speed. Right. And so that's probably one of the main reasons is the financial aspects that come around, and other people have voiced concern about the inherent bias in the coding of the AI systems that could cause problems as well. Yeah.
Two little things about Terminator.
Yeah.
I was at Caltech when Terminator came out, and a friend arranged a blind date for me and an actress who was in Terminator. It was Sarah Connor.
No way, Linda Hamilton?
And I was like,
get out of here.
Whoa. And then I found out, shortly after, I only saw her once, and that was it. But it was actually kind of a fun date. It was opening of the Olympics in LA that night. So anyway, I tell my students, and I kind of stretch it a little, that she actually had dated Arnold Schwarzenegger for a while they're filming, which I think happens a lot with movie stars.
Yeah.
And so I got a phone call a week or two after this date, and there's this voice at the end says, "You leave her alone, I break your neck like pencil." And they go, "Oh, is it Arnold Schwarzenegger?" I said, "I don't know. It could have been, or it could have been a friend of mine. I don't know, just trying to, jerk my chain or something." And then the other thing is, Arnold Schwarzenegger was on an interview, and he's going to be in a new movie about classical composers.
Oh, is he?
Yes. And he said, "I'll be back."
I've used that one for sure.
Okay. So, anyway, it's they're Terminator. Terminator was, I thought, actually a really good movie. And I think that's instilled the fear of us of AI. And that's what actually always comes to my mind when I get worried about AI. Is seeing the destruction.
Yeah.
And then of course the Matrix.
Yeah, the Matrix for sure. Yeah, those. You know what? I went and said that Terminator 2 is my favorite sci-fi, but it's pretty much tied with the Matrix. Those are my two. When I saw that movie for the first time, I was just blown away. We had to write a paper on it in my English class in college, so and analyze the movie. But yeah, whenever I think of that dystopian AI taking over, it's the scene in Terminator 2 where when they're driving down the desert, and Arnold Schwarzenegger is running down the history of how Skynet gets built and the funding bill gets passed. It becomes self-aware at August 29th at 8:18 a.m. or whatever the time is, and it's just so ahead of its time in that sense, and it's not inconceivable that could happen sometime in the future.
No, I agree.
Yeah, and the Matrix too. Eventually, I mean, we're tied to our phones. It's like that's the first step, right? And then you've got Neuralink, which is going to link us physically with our phones.
And Musk is working on that.
Yeah, and so that'll be like our link into the Matrix, and that's not too far off from it. If you can access information, at will. I mean, that's just the tip of the iceberg. Accessing information, and next could be projecting images inside of our minds, with our eyes closed, and that could be the start of it. So it's kind of scary to think about.
And then influencing others by doing that.
Right, exactly.
I think when I was driving over here, I was thinking about how, for example, states are suing oil producers for pollution and climate change and stuff like that now. And then I was thinking, we should sue Hollywood or places for deception. And then I thought, maybe we need AI to be able to distinguish when something is altered or isn't altered. Because I was thinking, if you take just out of context quotes,
right?
And I think a lot of times different media sources like to do that.
For sure.
But have a way of identifying, okay, this was taken out of context, and then finding what was the full quote and putting it back in and seeing what that says, because I think that's going to help us make rational decisions. So, I mean, there's some good uses, maybe potentially, but I just still
you'll need to
not have
and you need to find good uses to outweigh the bad uses, the bad things that it can create. For example, like deepfakes, the fact that AI can create these. I've seen this. There's a YouTube channel where this guy recreates famous movie scenes, but puts other actors' faces on them. So there's The Shining instead of Jack Nicholson, it's Jim Carrey, and it's the only thing that he hadn't mastered. And this was a year and a half ago when he was doing these videos, was the voice. But now we can completely recreate the voice of somebody speaking, their cadence and everything like that. So we have digitized people like William Shatner has digitized himself.
Wow.
And digitizing yourself so that he could essentially record himself and have conversations or send messages to his great grandchildren, and then they're like, "Hey, William Shatner," or something similar to like, Kal-El's, Superman's dad in the movie where he's talking to him, as a hologram, but still him,
Yeah.
So these deepfake videos are you need AI to tell you whether or not the deepfake is a deepfake or not now, because it's to the point to where you can't even tell. And so what that can be used for, just to manipulate societies,
right? Right.
And that's the really scary part about what it could do. Because I think that's honestly the biggest threat. Like, the idea of, AI becoming sentient and then, creating a lab of robots to take over. I think that's the more like in your face kind of thing. I think the truer one will be the deceptive one, right? The ones that the thing that we don't see coming. And I think it's going to be guised as untruths or deception as to what the truth is via deep fakes.
Yeah.
Yeah. Fun times.
And it's happening so
quickly. Yeah.
That's the scary thing. Everything has just been so quick now.
Yeah. And I'd like to have a way to, we're doing everything we can to extend life to see where the world's going to be, or I'd like to do that so I can see where the world's going to be in 50, 60, 70, 80 years, and where we were. Like if you dropped, like you're talking about Bach, for example, or a classical composer. I was thinking about this when I was delving down some music history, but if you dropped a composer or anybody from 1450 or 1500s, whatever, and you just dropped them in today, there would be so many questions, and they would be completely overwhelmed. They would not be able to function in society today. They would just not understand it. It'd be a completely different world. The stimulus that I get from being on my phone and being kind of addicted to the phone sometimes, to social media and stuff like that, and trying to shake myself away from that world, which is not even a real world. It's like this made up world, right? I can only imagine somebody who's coming in from a time where there was no electricity, no cars, no phones that could answer every question, and so I can only imagine if it's moving at this exponential pace where it's going to be in 20 years, especially with AI. Right. Editing this podcast, for example. So it used to take hours for people to cut from one camera to the other. And I have, it's an Autopod, it's an AI software that knows when to cut between cameras, essentially.
Wow.
And it does what used to take 2 or 3 hours for editors to do now takes like 60 seconds.
Wow.
Yeah, it's incredible. And so it goes back to the whole, people losing jobs. That aspect of it, so long as we can kind of adapt, is one thing. Like our economy can adapt one way, because we need to adapt one way or another, right? Like we've had to adapt to, cars coming out, the horse and buggy business going bye-bye, So at some point we need to adapt, but when it gets to the point to where we can't catch up with the rate of change is what could be the problem. Yeah. Well, thanks so much for coming. Thanks so much for this conversation. I had a great time.
Yeah, no, this was a lot of fun. I hope maybe sometime you'll have more questions in the future.
Absolutely. Do this again. Yeah, I appreciate it. Thank you.